Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about shock waves, normal and oblique. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comments section or reach out to me via the email provided in my profile. Shock waves. When studying supersonic flow, one of the most important phenomena we encounter is the formation of shock waves. These waves appear when an object moves faster than the speed of sound and the gas around it is forced to compress abruptly. Unlike smooth compressible flow, shock waves are thin regions, so thin that they almost look like a sharp boundary, where properties of the gas such as pressure, temperature, and density change dramatically over a very short distance. Scientists describe this as a high gradient region, which means that large variations in these properties occur within a very small space. To understand shock waves, let's start with the behavior of gases at different flow speeds. When an object moves through a gas at a speed much less than the speed of sound, the gas density remains practically constant. In this regime, the flow of gas can be analyzed using simple conservation of momentum and energy. As the object approaches the speed of sound, however, compressibility effects become important. This means the density of the gas no longer remains constant, but instead varies locally as the gas molecules are compressed around the object. For flows that are compressible but involve little turning of the gas, small deflections, the process is still reversible and the entropy, which is a measure of disorder, remains constant. This condition is described by the so-called isentropic relations. Isentropic simply means that entropy does not change. But once the object surpasses the speed of sound, and there is an abrupt change in flow area, such as at a sharp corner or wedge, the process becomes irreversible. Entropy increases and a shock wave forms. Across a shock wave, several things happen almost instantaneously. The static pressure, temperature, and gas density increase sharply. At the same time, the Mach number, the ratio of object speed to sound speed, and the flow velocity decrease. However, because a shock wave does not perform work on the gas, and there is no heat addition, the total enthalpy and the total temperature remain unchanged. This is why the ratio of total temperatures before and after the shock is always equal to 1. What does change, however, is the total pressure. The total pressure downstream of the shock is always less than the total pressure upstream. This loss of total pressure is an important consequence of shock waves and is a clear indication that the process is non-isentropic. Because of this, we cannot apply the simple form of Bernoulli's equation, which assumes incompressible flow across a shock wave. Now, shock waves can be classified by their orientation relative to the flow direction. If the shock wave is perpendicular to the flow, it is called a normal shock. If the shock wave is inclined to the flow, it is called an oblique shock. Let's learn about each of them. Normal shock wave. A normal shock stands at a right angle, 90 degrees, to the airflow. In this case, the flow downstream of the shock always becomes subsonic, Mach number less than 1. Across the normal shock, the pressure, temperature, and density increase sharply, while the flow speed decreases significantly. However, this comes with a heavy penalty. There is a strong loss of total pressure, which reduces efficiency. Normal shocks usually appear when a supersonic flow is abruptly slowed down, such as inside the intake of a jet engine. Normal shock equations. Here ρ represents the density, P represents the pressure, T represents the temperature, total P represents the total pressure, total T represents the total temperature, M represents the Mach number, and R represents the wedge angle. These equations are valid for air with a ratio of specific heats, gamma, equal to 1.4, and are derived from conservation of mass, momentum, and energy, assuming one-dimensional flow and no heat addition. They apply to cases where the shock is perpendicular to the flow, or when the wedge angle is large enough that the oblique shock cannot remain attached. The temperature ratio T1 over T0 is equal to 7 times m squared minus 1 multiplied by m squared plus 5 and then divided by 36 times m squared. The pressure ratio P1 over P0 is equal to 7 times m squared minus 1 divided by 6. The density ratio ρ1 over ρ0 is equal to 6 times m squared divided by m squared plus 5. The downstream Mach number squared, m1 squared, is equal to m squared plus 5, divided by 7 times m squared minus 1. The total pressure ratio, total P1 over total P0, is equal to the quantity 6 times m squared divided by m squared plus 5 raised to the 7/2 power, multiplied by 6 divided by 7 times m squared minus 1 raised to the 5/2 power. The total temperature ratio, total T1 over total T0, is equal to 1. Oblique shock wave. An oblique shock, on the other hand, is tilted at an angle to the incoming flow. Here, the Mach number decreases across the shock, but the downstream flow often remains supersonic. This is known as the weak shock solution. In rare cases, the flow may become subsonic if the strong shock solution occurs, but in nature, the weak solution is far more common. Because the shock is slanted, the energy losses are smaller compared to a normal shock, making oblique shocks more efficient. These shocks commonly form when supersonic flow encounters a sharp wedge, a pointed nose, or the leading edge of a thin wing. Engineers deliberately design supersonic aircraft to take advantage of oblique shocks to control high-speed flows efficiently. Transition from normal to oblique shocks. When a supersonic flow encounters a wedge or a sharp deflection, the type of shock depends on the wedge angle and the Mach number. If the wedge angle is small enough, the shock wave attaches itself to the wedge and becomes oblique. If the wedge angle is too large, the shock detaches and forms a normal shock in front of the object. Thus, the equations for normal shocks apply only when the wedge angle exceeds a certain critical value for a given Mach number. For smaller wedge angles, oblique shock equations must be used. Oblique shock equations. Here ρ represents the density, P represents the static pressure, T represents the temperature, total P represents the total pressure, M represents the Mach number, R represents the wedge angle, and S represents the shock angle. These equations are derived under the same assumptions as the normal shock equations, compressible. In viscid adiabatic flow with gamma equal to 1.4, but are specialized for a two-dimensional wedge flow where the shock is inclined at an angle S to the flow direction. The shock relation is the cotangent of A equals the tangent of S multiplied by the quantity 6 times m squared divided by 5 times the quantity m squared times the sine squared of S minus 1 close quantity minus 1. The temperature ratio T1 over T0 is equal to the quantity 7 times m squared times the sine squared of S minus 1 multiplied by the quantity m squared times the sine squared of S plus 5, all divided by 36 times m squared times the sine squared of S. The pressure ratio P1 over P0 is equal to 7 times m squared times the sine squared of S minus 1 divided by 6. The density ratio ρ1 over ρ0 is equal to 6 times m squared times the sine squared of s divided by m squared times the sine squared of s plus 5. The Mach number relation is m1 squared times the sine squared of the quantity s minus a closed quantity equals the quantity m squared times the sine squared of s plus 5 divided by the quantity 7 times m squared times the sine squared of s minus 1. The total pressure ratio, total P1 over total P0, is equal to the quantity 6 times m squared times the sine squared of s divided by the quantity m squared times the sine squared of s plus 5 raised to the 7/2 power multiplied by the quantity 6 divided by 7 times m squared times the sine squared of s minus 1 raised to the 5/2 power. For oblique shocks, the outcome can be either a weak shock solution, where the downstream flow remains supersonic, or a strong shock solution, where the downstream flow becomes subsonic. In nature, the weak shock solution is much more common, but in certain conditions the strong shock can occur. In practice, these equations help engineers predict how the air will behave when a supersonic flow encounters a wedge, a sharp surface, or a sudden change in geometry. For example, they are essential in the design of supersonic inlets on aircraft and rockets, where shocks must be carefully managed to slow down the incoming air for the engine to operate efficiently. If uncontrolled, shocks can cause major losses in performance or even dangerous conditions such as engine stall. Similarly, in aerospace reentry problems, oblique shocks and normal shocks determine how much heating occurs on a spacecraft's surface. Shock waves are not just abstract mathematical entities. They directly influence whether high-speed flight and space travel are possible. Okay guys, now let's have a little quiz. The quiz consists of 3 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What happens to the downstream flow after a normal shock wave? The correct answer is it becomes subsonic. Question 2. In an oblique shock wave, under which condition can the downstream flow remain supersonic? The correct answer is only in the weak shock solution. Question 3. Across a shock wave, how do total pressure and total temperature change? The correct answer is total temperature remains constant, while total pressure decreases. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, These courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about wave and flow phenomena, Doppler effect, and isentropic relationships. See you in the next video. Bye.